Welcome to today's class on real analysis. The first chapter of your syllabus deals with basic topology. So today we discuss some definitions of finite sets, infinite sets, etc. So let us start with some definitions. So first we define a function. Consider two sets A and B whose elements may be any objects whatsoever, and suppose that with each element x of A there is associated in some manner an element of B, which we denote by f of x. Then f is said to be a function from A to B, or a mapping from A to B. Now we define domain and range of a function. The set A is called the domain of f. So you know that f is a function from A to B. So A is called the domain of f. We also say that f is defined on A. And the elements f of x are called the values of f. The set of all values of f is called the range of f. Now we define onto function, for which first of all we define what is the image of E subset of A under f. That is, what is f of E. Let A and B be two sets and let f be a mapping of A into B. If E is contained in A, f of E is defined to be set of all elements f of x for x belongs to E. We call f of E the image of E under f. In this notation, f of A is the range of f, and it is clear that f of A is contained in B. If f of A equal to B, we say that f maps A onto B. Note that according to this usage, onto is more specific than into. Now we define inverse image. If E is contained in B, f inverse of it denotes the set of all x in A such that f of x belongs to E. We call f inverse of E the inverse image of E under f. If y belongs to B, f inverse of y is the set of all x in A such that f of x is equal to y. Now we define one-to-one mapping. So this is the definition. If for each y in B, f inverse of y consists of at most one element of A, then f is said to be a one-to-one mapping of A into B. This may also be expressed as follows. F is a one-to-one mapping of A into B provided that f of x1 not equal to f of x2 whenever x1 not equal to x2 for x1 in A, x2 in A. The notation x1 not equal to x2 means that x1 and x2 are distinct elements. Otherwise, we write x1 equal to x2. Now we define equivalent sets and equivalence relation. If there exists a one-to-one mapping of A into B, we say that A and B can be put in one-to-one correspondence, or that A and B have the same cardinal number, or we say that A and B are equivalent, and we write A tilde B and it is read as A is equivalent to B. And this relation has the following properties. 1. It is reflexive, that is A is equivalent to A. It is symmetric, that is if A is equivalent to B, then B is equivalent to A. It is transitive, that is if A is equivalent to B and B is equivalent to C, then A is equivalent to C. Any relation with these three properties is called an equivalence relation. Now we are going to define finite sets, infinite sets, countable sets, uncountable sets, and at most countable sets. For any positive integer n, let Jn be the set whose elements are the integers 1, 2, etc. n, and let J be the set consisting of all positive integers. For any set A, we say that A is finite if A is equivalent to Jn for some n, and empty set is usually considered to be finite. And A is infinite if A is not finite. A is said to be countable if A is equivalent to J. Remember that J is a set of all positive integers. So a set A is countable if that set is equivalent to set of all positive integers. So A is countable if A is equivalent to J. And A is said to be uncountable if it is neither finite nor countable. And A is at most countable if A is finite or countable. A is uncountable if A is neither finite nor countable. A is at most countable if A is finite or countable. Now we have some remarks. Countable sets are sometimes called enumerable or denumerable. For two finite sets A and B, evidently we have A is equivalent to B if and only if A and B contain the same number of elements. But for infinite set, the idea of having the same number of elements becomes quite vague, whereas the notion of one-to-one correspondence retains its clarity. A finite set cannot be equivalent to one of its proper subsets. This is trivial. So this is one of the interesting property of infinite sets, that is, an infinite set is equivalent to one of its proper subsets. So this is possible. So you consider an infinite set, it is possible that that set is equivalent to its proper subset. So that we can illustrate using an example. Now we can give an example to show that an infinite set is equivalent to one of its proper subsets. So for example, you let A be the set of all integers. First we show that A is countable. Consider the following arrangement of A and J, of A and G. You arrange A set of all integers like this: A equal to 0, 1, minus 1, 2, minus 2, 3, minus 3, etc. And you arrange J like this: 1, 2, 3, 4, 5, 6, 7, etc. Define f from J to A by f of n equal to n by 2 if n is even, and minus of n minus 1 by 2 if n is odd, so that f of 1 is 0, f of 2 is 1, f of 3 is minus of 3 minus 1 by 2, so this is minus 1, f of 4 is 2, f of 5 is minus of 5 minus 1 by 2, it is minus 2, etc. That is, f defines a one-to-one correspondence between A and J. F defines a one-to-one correspondence between A and J. Therefore, A is countable. And you observe that J is actually contained in A. That is, A is equivalent to one of its proper subset J. Remember that A is a set of all integers. A is actually a set of all integers, whereas J is set of positive integers. So clearly J is contained in set. So set is actually A. Sorry, this shows that A is equivalent to one of its proper subset J. So it is possible that an infinite set is equivalent to one of its proper subsets. So using the above observation, we can redefine infinite set as a set A is infinite if A is equivalent to one of its proper subsets. So that's all for today. Have a nice day.